Okay, so we have a couple of more applications to integration, and now we're going to do something we haven't done yet. So far, integration has always been about areas, but you see here now the word is volumes. We're going to do, in other words, three-dimensional objects. And it might be strange that you can do this with integration too. So before we discuss this, let me very, very quickly review how the area part worked. We discussed it last time, but I want to look at it a bit differently again. So we have a function, f of x, and we have a certain domain on which this function is continuous. These are the conditions that we need. And how did we integrate them? So we said, okay, remember this from, go look it up on the beginning of the lectures. We would take, you look at a particular x here, and you build a strip exactly as high as the function value. So this would be the function value. So this would be f of x, right? And then you make the strip very narrow. Now, of course, I cannot draw this. I'm going to make it much... I should have chosen it a little bit. I'm sorry. Allow me to... okay, sorry. My picture is a little bit... I went in a place where it's hard to see what happens. So let me do the picture over again. So here is my curve. I'll do the curve a little bit nicer like this. And so here we have our x. Let's put the x a little bit here. And so this, as I said, would be f of x. And we're going to build a strip. So a strip exactly as high as, this is supposed to be horizontal, as the function value. And the width of this strip we call delta x. And what would you say then? Okay, so first of all, what's the area of a strip? That's just a rectangle, so that would be height times width, right? So that would be, the height is f of x, that's what we said we make it, and delta x is its width. And then the idea was that we do this, if we have this interval here from A to B, we making these strips, we make copies of these strips like all over the place, and we add them all up. And this is for on this interval, which we can denote somehow in that. Now, that gave us the area of this strip. So the area, let's call it just area. But of course, not really. It's only approximately so, because we have flattened here. Each time we make a strip like that, we flatten, and sometimes we have overcut tally, this black part, that would be we counting too much. Here, for instance, we would have undercounted. So there's an undercount. So we cannot really say it's exactly the same. That's why the twiggly is. But how do we get equality? Well, we get better measurements by making delta x smaller, because then the straightening will have less and less. Will be, if we have a curvature like that and you straighten here, okay, you lose a lot. If you make it much smaller, you lose much less, right? This is much less that you use. So the idea is that if we take a limit here for delta x going to 0, then we get actual equal. Okay, that's just how it went. And then we had the notation for such a thing. We call this a Riemann sum. I'm just saying that because it's a word that I can use once in a while. A Riemann sum, Riemann is the name of a person, and he described this method, although the method goes back to Newton, which is more than a century before Riemann. So what is a Riemann sum? It's a summation here of which you take a limit. And we had a notation for that. We said, okay, if you take the limit, everything, the straight lines become like, this sigma becomes an elongated S. This A and B would become then the endpoints here. We have this fx, and also this delta x, this width, becomes something that we call a dx, an infinitesimal. Okay, so that's how we went for areas. Okay, so what we want to do now is basically a little bit the same. Let's look at the volume. So I'm going to have to look at some pictures. I look at some pictures from the book here. So here is the top you see here. I cannot point. Can I point here? Wait, okay, I think I can. What I can do here. I can make some. So we look at this volume. It's a solid, right? A solid means a three-dimensional object which would, solid meaning we think of it as a block of wood or something like that, and we want to calculate its volume. So what we're going to do is a little bit the same. Is we're going to subdivide it, and here, so here, what you see here is one of these strips. So I'm going to take a little bit different notation. I call this x, and this was the height of the strip. It's a little bit on a slanted angle to give the impression that we're three-dimensional. Okay, so that's why it's not a straight thing. And so, and this would then be the delta x. Okay, so again, we do the same thing. We build a strip. Now, so the question is now, what's the volume of that? Well, it's no longer a strip now, right? We now get a block. Okay, so let me go back to a picture. The picture here is not very enlightening, so I'll make my own picture. Sorry, here. So we have, although I'm very bad at drawing, so we have here a three-dimensional object. So there are 3 dimensions here, so we have some object here. Okay, it's 3-dimensional, right? So it has some width also like that. And so, okay, we have x here. It's on a certain interval. Let me not concentrate on the interval. Let's concentrate on the x here. So we're going to cut this. We're going to slice this. Okay, we make a slice. So, okay, here we see an example of a slicing. Can I get rid of this? I guess I have to get rid of this way. So, sorry, I guess, yeah. No, where is the slicing here? No, it was before here, sorry. Here, right. So here's another volume. Here's like a half cylinder, like one of these hangers or something like that. And you see here we have, sorry, shoot. I jumped all the way back. Oh, I'm sorry, guys. Now I have to find this. It's 7.2. Here it is. So let me do the annotate again. So we have here, this is what we slice with. So here you would think of this as, this plane is located at position x. It's not really a plane, it has a certain thickness. So, okay, the thickness here, we're going to go delta x. And so we slice. Now, in the case of a cylinder, of course, we're going to get what we see here is this kind of slice, like half a slice. So you could think of this as in the deli when they cut salami, okay? And the machine cuts these salami slices, these salami slices for you. So they are not really flat, right? They are a little bit thick. And so, for instance, if you would slice a ham, say, or something a little bit more irregular, you're going to get something. Okay, let me go back to my picture here. You got something. So I'm going to now give. So here's a slice. So it's going to have a certain bend here. So it's going to look something like. So this is the outside rim, and then we have a backside here, but there's a certain curvature here, right? So imagine, look at a bigger slab of ham. You can imagine that the front side is slightly different than the back side because we have curvature, okay? But what we'll do, we would have this here too, right? We had this black curve that would run here. Okay, I should make a black curve. The black curve would be curved. So our red slice is curvature, but we're gonna straighten it. So I'm gonna straighten this here, flatten this out. So in other words, if you think of this slab ham, you cut the sides clean so that you have a very nice, basically very flat pancake type of thing. And then you get this blue nice cylinder, very small cylinder, okay? So we get a cylinder, and what is the cylinder? We can much better calculate the area for. So the blue part here, so this volume, what is the volume of this cylinder? Volume of the cylinder, or rather perhaps let's not call it cylinder, let's call it slice. The volume of this slice here. Well, if you would lay it flat, so it would be like something like that, right? So we would lay it flat here on its side. So I'm very bad at drawing, sorry guys. That is really a picture that does nothing, worth nothing. Okay, so here's, no, sorry, this is very bad. Let me try, give me one more try to it. Okay, so this is the top part of the slice, and then there's the bottom part of the slice is almost the same. Okay, because we straightened it. So this is the thickness of the slice here. I hope you can see what I'm trying to do here. Now it's a cylinder, so what is the volume of a cylinder? Now, if it would be a cylinder, now the base, you see the base is very irregular. If it would be a true cylinder, then it would be something like this, right? So you would have some object like that, and we know the area of a cylinder. The formula is you take the area of you have a radius r here, and so you do pi r squared, that is the area of the bottom part, which is also the same as the top part, and you multiply this with the height. This is the height of the cylinder. So that's the volume of a cylinder. Now, what is this pi r squared? Well, pi r squared is the area of the cylinder here. Of the circle, sorry, of the disc, the bottom part. Now, the same formula is true if you work with an irregular cylinder like this. Okay, so that what that means is you have this bottom curve here, and then on top of that you build like you go like 1 centimeter up all the place, and you get a slab. What is the volume of a slab? It is just the area. So the area of this bottom part or top part, sorry, I'm saying it the wrong way. This is the top part, right? It's the area of the top part times the height, this, or the thickness perhaps. That's perhaps the better way to say it, okay? Okay, so let's see now. What would this be in our setup? So what is our setup here? We have this slice here, and we have made it a certain thickness. So the thickness here, well, it was blue. Let me take the blue thickness. So this distance here, we call this as before delta x. Okay, it's the thickness of this thing, and we're going to make this thinner and thinner, always slice thinner and thinner, so that in the end we get a limit. We will get a real equality. Okay, so what does this correspond in my picture here? Think about it. Which of these two is delta x? Well, it's if you put this picture here down and make it look like this, you see that this is the delta x, right? And this is just the area. So a of x, I'm going to write this, a of x is the area of the slice. Okay, so when I slice somewhere, I get a certain cross section, and the area of the slice, or if you want, the cross section. Okay, and so what we have now, we have the summation of all these x's that again on a certain interval, ax delta x. Now that is the volume, but not really, because remember one thing I said I would do, the difference between the red and the blue, well, it's no longer visible, but my blue was supposed to be straightened, right? Whereas the red was somehow following the curvature of the object. So in order to have real equality, what we need to do is I have to take a limit here. So the volume is equal to the limit, and what by making this always smaller and smaller, so the delta x going to 0. But look at this. This is a Riemann sum again. Remember, I called Riemann sum. I gave a name for it just because I see it again here. Here's the Riemann sum. It's the same form, except the function is different. Now, that was f of x. Here it is a of x. So we know what this represents. We know it represents an integral from a to b, the endpoints, of what the function is now a of x. And we integrate now. That tells me the infinitesimal. Okay, so this is the formula that we propose for the volume of an object, but it is not a good formula, because this function here, ax, might be very difficult to calculate. I mean, so at every x you're going to have to take a slice. So I remind you, this is what the slice is here, right? So okay, if you do this with a cylinder of half a cylinder here, it's very easy. You know that the slice is a nice circle. But imagine if you do this with the next object. I guess I have to. If you do this with this object, the slices, okay, they are still some weird parallelograms or whatever it is, I don't know what they are, but if you slice them, they change, okay? It's a function, and you could perhaps sometimes calculate this. Now, we're not going to do that. There are examples in the book, but I'm not going to do that, because the formula that I have so far is not going to be useful for me. In very special cases, you can use it. But let's skip those cases and let's go to what we really need. And that is, we're going to look at special three-dimensional objects, solids. And we're going to look at solids of resolution, of revolution. What do I mean with that? So revolution here, it's not that we're going to start a new civil war, but what I mean here is revolving, turning around. Again, big pictures help a little bit more. So let's look here at this picture here. Okay, so on the sorry, this. So we start with the same thing. We have a function. Let's call this f of x. This we have f of x, and it's on a certain interval, say from a to b. Or let me take the interval as it has been shaded. Okay, so we have this is a here and this is b, say. Okay, now we can calculate the area of this thing, but that's not what we're going to do. Look what we're going to do. Now this is two-dimensional. Now imagine, so the next picture shows you kind of the same picture in a three-dimensional setup, and you see what we're going to start doing is we're going to turn this region, this part here, think of that as, I don't know, as a wooden or a cardboard cutout, and then we're going to turn this around this axis. So here you see half of this movement that we've done, and here's the full movement. Okay, so that's what we mean with a solid of revolution. This is when a region that we take is being turned around an axis, which is in this case the x-axis. We will also take other axes, but for now the x-axis, and we produce a solid of revolution by turning it around. Okay, so here is another example, the same thing, where we here we have a concrete example, so we can work a little bit with a concrete example. So we would have somewhere an x here. We would take this little strip. Yeah, no, sorry, that's not. Sorry, that's not what I meant to say. So yeah, sorry. I have an undo button here too. Okay, yeah. So we take this region again and we return it around the x-axis, and I hope you see that is the object you get here. Okay, so what we need now? Now remember from our previous formula, I'm not going to, well, okay, let me go back here to my formula. My previous formula, this is what we need to calculate. Okay, so we have this region. Let me do it here. We have this region here, f of x, on a certain a to b. For simplicity, I'm taking the region above the x-axis. So this is a region that I'm now going to rotate around the x-axis. So I put myself in three-dimensional setup and then rotate it, and I get what I guess a kind of vase, where these are the sides of the vase. This would the base of the vase, and this will be the top of the vase, become the top of the vase, right? Okay. Now what do we need? So this, okay, so the picture therefore is something, we get circles here, right? Every of these things get turned around, and then we have a similar thing here, and then so imagine these lines here, they connect here, and so okay, it's getting. As I told you, I'm very bad in drawing. I hope you can see still that we get something like a vase like that. Okay, so what we need is this function ax. How did we get that? Well, you make a slice. Okay, so we would take somewhere an x here, and we put a plane that goes through x, and well, a plane that goes to this x, and it will cut this slice in a circle, right? Because every point here on the curve is turned around along a circle, and so we take one of these points here. This, well, my picture is a little bit off. My x is here, really. So we take this x here, this point on top of the region, and we turn it around. Okay, so the cross section, the slice we get is a circle. That's good. That's good news, because I have the formula ax. I know the area of a circle. because remember this AX is the area, well, it's here, right? AX is the area of the slice. And in case it's a circle, I only need to know the radius. What is the radius here? Well, let's think about it. It's this distance, right? That's the radius. What is this distance? Well, it's given by the function f, right? Because we go just exactly to fx. So the radius here is f of x, and therefore the formula is pi fx squared. Okay, so let's put this in the formula. So here we have our first, this formula, as I said, is not something we're going to use, but this is the formula we're going to use. So this is the formula for the volume of a region rotated around the x-axis. Okay, later on I'm going to give this, there are two different methods we'll do. This method will be called the washer method, but I'll explain this later. So I'm going to call this later volume of the washer method, but let's now just call it the volume. Okay, so it is from A to B, and then we have A of x, that is pi fx squared, that's this formula, and then dx. So that's what we do. Okay, let's do this. It helps if I do this on an example. Let's take, what you want to do, a parabola? Okay, so y is x squared, okay, and let's take from 0 to 1. So we're taking this region, and now I'm going to rotate this around along the x-axis. So what you get is some kind of, yeah, I don't know what you describe it, a kind of a tag, weird form thing. I don't even know what to call it. So, but we can write out the formula very easily. Okay, what do we do? Well, first of all, the endpoints. Well, that's 0 to 1. There's a pi here, which I can take out. So I'm going to, in the formula, put my pi out. Remember, the pi came from the formula for the, that's not what I wanted to do. The pi came from the formula for the area of a circle, right? So we have a pi here, then fx. What is fx? Well, fx is x squared, be careful. So that is the thing that we have to square, and then we have to integrate. That's it. So once you set it up, it's very simple. So this is 0, 1, x to the 4th dx. So that would be pi x to the 5th over 5 power rule between 0 and 1. You plug in, that's pi, don't forget the pi here, 1 over 5 minus 0, so pi over 5. Kind of cute, right? Why is this? Would you think that if you look at this area and then you start rotating it around, you get this weird, I don't know what to call it, that you get a pi over 5? Okay. So, but we can, let's do another example. Well, no, let's now make this a little bit more interesting, okay? So the first, what I was describing was, I said, okay, I have a region, and then this here is the region. So we have this region here. Okay. Why is it? Oh no, there's this one. So we have this region along a curve that we then rotate around the x-axis, and then we get a volume, a solid, and the formula for the solid is given by this formula here. Sorry, where's my formula? Where did my formula go? Ah, here, this formula, okay? What I want to do is, first of all, this is still a little bit of an, I don't know, right? This is not a really true geometric object. It is all these straight lines here, this cutoff here, a cutoff there, and a straight there. We discussed this in 2.1. So what we really would like to do is, what if we have a region, like here, we have one curve, f of x, and we have another curve, for the simplicity, let's say it only intersects, so this is f of x, this is f of x, this is u of x. We get an intersection here, we get this region, okay, and this is, say, somewhere in an x-axis system, and now we're going to rotate this around the x-axis. That's a much more interesting object, right? We get now something that is hollowed out, right? If you would rotate this around, so think about this, the black thing is cardboard, and now you take the cardboard and move it out of the plane and turn around 360 degrees until you're back where you were, and you look at all the positions together, all the positions that you had, this forms a solid. And so we want to now calculate the area of the volume of that solid. But it's kind of obvious what we should do, right? Because, okay, let's think about it again. In the formula, we needed the area of the cross section. Okay, let's look. Now we know that the cross sections because we turn things around, we rotate the thing around. So if you have, here is my x. So here is this little strip that is built on top of x. So I'm going to make it a little bit bigger, but not too much. If I rotate this around, if inside the actual object, the solid, this point here, for instance, is rotated on a big circle, right? It goes all the way around like that, 360 degrees. I mean, the circle comes out of the picture, right? It's a three-dimensional thing. I'm rotating. I hope that you understand, right? The red is something that is actually in the third dimension, right? This is in this third dimension that the red circle is. So this point is turned around in a red circle. And what is the radius of that circle? Well, it is the function value, right? It's actually all the way up here. This is f of x. So this is f of x. Let me write it here. This is f of x. Now what happens to the... There's another point that we would like to look at. What happens to this point? Well, this time the radius of this point will lie on this circle, right? Inside the rotated solid. So this would be g of x. So what we get is, okay, so if I intersect this, I get, now look at this. So this is a two-dimensional, this now is sticking out of the plane, right? And this is what what is it? It's a disc with a hole in. We call this a washer. I mean, like if you put in, for those that have ever done some construction or screwed, and you know that washers, they look a bit like that. In my days, by the way, tokens look like, Sopwith tokens still existed and they looked like that, but okay, that's a long time ago. So this is a washer. And so what we need to know is what's the area of that washer, right? That's the cross section. So the cross section, so this cross section here is a washer. So what's the area of a washer? But okay, it's a circle minus a circle. So the area is we have an outer radius, the red one, that's the big outer radius, right, of this thing. So we call this r out, this distance, which in this case is f of x. So r of x is out of x, r out is r of x. The outer, with r out, I mean the outer radius. This distance we call r inner, the inner radius of the inner circle, of this inner circle. Okay, so it is A is pi r outer squared. That's the area of the big red disk. I should perhaps, let me make it in red. So the red one would be pi r outer squared. And what do we do now? We subtract, right? We do minus pi r inner squared. This is a area of a disk, the big disk, and from that I subtract the small disk because it's removed. Okay? Okay, so that's the general formula, but we have actually, we know what it are, this f and g, so let's put this in. So this is actually pi f square minus pi g square. So the formula here, so the area, no, not area, volume. So now we're getting to our first real formula, the volume of the washer method. So using the washer method, the formula is, this was from A to B, we have pi f squared minus pi g squared. That is the function A, and we just had to integrate that. Remember, this is, here. This is so-called the slicing method. Okay, that's it. Now, we can make this slightly compacter by putting the pi out. So this is f squared minus g squared dx. So what is this f and g? Well, f and g, as you see, are, if you go back now to the black picture, I don't know whether I can get, well, I can perhaps get a little bit of the back picture. I'll try to get. So let's look at what we originally started with. We had this region, right, that we were turning around. And so what is f here? F was the top curve, and g was the bottom curve. So when we get this formula, that's basically what we do. So we are in the same situation as we were in the previous setup in 2.1 on area of a curve. We had to determine what was the top one and what was the bottom one. Okay, so let's see. I want to do an example here. have one, otherwise I just... Yeah, let me just make up an example here. So suppose we have two functions. So okay, so how does the question in test and so look like? But let me write it up in that way. So we have so find the volume of the region rotated around the x-axis between y equals radical x and y equals x squared. So I'm going to make a picture, but we don't need to make pictures, remember. On the interval, sorry, on, yeah, let me do an interval. Sometimes we don't have an interval and then we do intersection, right? So when we have a situation in that, we would have to calculate the intersection points, but sometimes they give the stuff. So for simplicity, I'm going to say on the interval from 1 to 2, just so that we have something. Okay, so this is how a question would look like. I mean, as I said, it could be that I give two curves and you have to find intersection points, but okay. So what is, you can make a picture, it's not necessary, but let me, just that we see what is going on. We have, this is radical x, and this is x squared. And actually they intersect here at x equals 1. Yeah, okay, so perhaps, no, okay, it's better perhaps to do this example, sorry. Let's just do this without an interval. So find the volume of region rotated around an axis between these two curves. So we have the one curve is the curve radical x, and the other one is x squared, the parabola. And so we do need to find the intersection points, and then we have this region. So let's work it out. Step 1. I was going to do an intermediate example, but let's go to the thing that we really want to do. Okay. Step 1 is the intersection points. So it starts off basically the same as in the previous section. So we have to find the intersection point. That we do that by putting these two equal to each other. Now, to get rid of a radical, we square both sides. We get x is equal to x to the 4th. So we have to factor this. X to the 4th minus x equals 0. We can factor out an x. We have an x cubed minus 1 equals 0. Now, this is not so easy perhaps to factor anymore, unless you notice that we have a difference of cubes. You can actually factor out an x minus 1, and what is left is an x squared plus x plus 1. Okay? I'm going to do this here. I'm not going to explain how you do this factoring. I'll give you things where the factorization is more obvious how to do. But so why do I know that x minus 1 is a factor? Well, this factor is at least, you know that x minus 1 is a factor because if I plug in 1, I get 1 minus 1 is 0. Okay, that's how you know that there is a factor. And how do I find this factor? By long division. Okay, that's how it works, but I don't want to explain everything. Now, this is a quadratic irreducible. You remember those from integration by partial fractions? So this means it has no solutions. So there's only two solutions, x equals 0 and x equals 1. Because this is never 0. Okay, if you don't believe me, try to do with the quadratic formula, and you see that you get only imaginary complex numbers that are solutions. So we have two solutions. So step 2, there are two intersection points, like you see on the picture, right? So what we do next is a table. So we make a table. Why do we make the table? Remember, we're making the table so that we know which one of the two is on top. Well, you see it on the picture, but suppose you don't. So let's work it out completely algebraically. So I have to take a test point somewhere between 0 and 1. Everybody's going to take a half, right? I'm going to take 1/4. Why do I take 1/4? Because I know what the square root of 1/4 is. The square root of 1/4 is a half. I also know what the square of 1/4 is, that's 1/16. So this is the bigger number. If you take 1/2, then you have a bit harder time, right? You have the calculator. You can always use calculators, of course. So it is clear that this is the top curve, and this is going to be the bottom curve. So in my formula, remember, so this is the formula that we will use most of the time, but I should actually really write a formula like this. The volume of a washer, using the washer method, is, okay, AB by R outer squared minus pi inner squared. And so what we need to find out is what is our outer, what is our inner, which in this case is these functions f and g. This is in our outer will be the top curve, our inner will be the bottom curve. Okay, so in our formula, so let's copy the formula again. The formula says the volume of a washer, well, just to put the washer here, from 0 to 1, we take, well, we can put the pi out, we take the square of the top of the outer one, right? It's this, yeah, let's put the pi out here, then it doesn't distract us. It doesn't distract us. So we take the square of the outer one, which was radical x, so radical x squared, and subtract the square of this one, minus x squared dx. And that's it, we're done. So it is pi, and then we have, well, this is just x, and this is just x to the fourth, right? So we have to integrate this. And that, well, we don't have to write it anymore, right? Let's integrate it. And then the derivative of x is x squared over 2, and the derivative of x to the fourth is x to the fifth over 5, and that is between 0 and 1. If I plug in 0, nothing happens. So the top point gives me pi 1/2 minus 1/5, and if I plug in 0, I get 0 there. So that's the answer. If you want to put this on common denominator 10, so what you have on top then, you have a 5 minus 2, 3. But it's not necessary. You can leave it like this. Okay. All right, that's how this works. And so in problems now, I'm going to give you a couple of those homework problems. Okay, let me see here. Right. Okay, I want to give me 1 sec here. I want to double check something. Okay. Yeah, this is a new textbook, I told you, so I don't always know exactly what they do. And it seems that they are not covering the case of, I said we would look at different axes. I'm not going to deal with the rotation around the y-axis today. That will be the lecture for next time. Okay, so this is how far I will go today. And so this, we have now a general formula here that this is this formula, if you want, here, that we're going to use, and where f is the top curve and g is the bottom curve. Okay, and the rest I'll let you work out, and then we'll do some review and some quizzes on that.